Hi everyone, my name is Jarett DeAngelis and I'm a scientific systems engineer at BioTeam. BioTeam is a scientific consulting firm specializing in connecting biomedical researchers with solutions that help them use technology to broaden the scope and accelerate the pace of science. You could say that we're the SEAL Team 6 of scientific computing. Like, we're definitely too modest to say that ourselves, but we wouldn't stop you. So, in this video, we'll talk a little bit about shared resources in high-performance computing. We'll give a brief overview of the concepts, and at the end of the video, I'll provide some links for further exploration and research. Let's dive in. High-performance computing refers to the practice of linking some number of computers together in order to collect their computing power to solve some large problem that would be prohibitively difficult to solve on just one machine. One classic example is weather modeling. It's possible to do simulations that give estimations of how likely it is it'll rain where you live on a regular desktop computer, but it would take a very, very long time to run that simulation. So instead, weather centers use HPC to lash together the CPUs, memory, and storage of many computers at once in order to get the job done much more quickly. To enable that kind of work, we use HPC software to get CPUs and memory to work together across machines and across parallel or network storage systems in order to make it possible for many computers to work on the same data at once. So first, let's talk about MPI. MPI stands for Message Passing Interface, which is a fancy way of referring to software that permits computers to send data structures to each other over a fast network and for the purpose of sharing memory. When we design HPC systems, one of the first things we think about is the speed and capacity of the network being used to link their components together. Programming libraries like OpenMPI and MPICH are used to run programs that use that network to use much more memory at once than would be possible on a single computer. So when a programmer wants to be able to use memory this way, they'll use an MPI programming library to create, send, and receive data structures to and from other nodes in the HPC network, letting the other nodes perform work as needed on the data and later reassembling it as the problem is solved. In this diagram, the compute nodes use that fast HPC network, usually running at least 10 gigabit as opposed to consumer 1 gigabit networking, as a way of passing messages between each other to permit these big problems to be solved. HPC storage solves a similar problem in a different way. You're probably already familiar with the concept of file systems. An example of a file system would be the NTFS file system available on a typical Windows computer that presents you with a drive letter, usually C, and directories or folders in which to store files. In HPC, we spread file systems out among many devices for the sake of speed and access for many computers. To get an idea of how this works, imagine using just one drive to store data in your computer. You already do this with a solid-state disk or NVMe device installed in your laptop, or even the built-in eMMC storage in your phone. And that device has a set amount of storage bandwidth, just like network bandwidth, available to it to get data and store it after computation. Storage devices are typically much faster than, say, a network connection. You can write to an average consumer SSD, for example, at around 400 megabytes per second. And by comparison, a reasonably fast internet connection might have a 300 megabit per second download speed. So with that difference between bits and bytes, that's over 8 times slower than the disk. And you might expect that given how easy it is to load a photo stored in your computer. But sometimes with HPC applications, speeds like 400 megabytes per second are just not fast enough. Or you might need to be able to do far more open and close operations on many files than you could typically do with a single SSD. And you might also need really big storage volumes, many terabytes of capacity or even petabytes, or over 1,000 terabytes. So that's where parallel and distributed file systems come in. Distributed file systems permit you to spread files across many devices, accessed over the HPC network with these access nodes, so that you can have lots of room on all those disks. And parallel file systems up the ante by spreading not just the files and other data structures across all those devices, but spreading the pieces of them across devices, such that every one of those network connections that connect the devices to the access nodes can get the data up from the devices to the compute nodes by leveraging all of that network bandwidth instead of being limited only to the bandwidth from one storage device. This trick is similar to what you get from a RAID array, redundant array of inexpensive disks, except it happens across many computers in a network instead of only across many devices in a single computer. It's cool stuff, right? Now here's the kicker. This actually isn't even all that hard to experiment with yourself. If you have as few as 3 old computers lying around and a few storage devices, you can build an HPC class file system in your living room by networking them together and using software like Ceph or Gluster, both open source parallel file systems, to build it. Ceph might actually be the easiest, provided you've got the hardware lying around. With the open source virtualization platform Proxmox, deploying Ceph on 3 machines networked together is as easy as clicking a few buttons. And we'll put links for this in the notes if you're curious. Well, we hope this was at least a little educational. We'll put some useful links for you to check out in our notes. Thank you, and happy HPCing.